Hey guys, Mrs. Traver here. We're going to do our last part of the notes on section 10.2, 10.3. So this is part 3 of 3. In the first section, we looked at simplifying radicals and adding and subtracting them. In the second section, we looked at multiplying radicals as well as distributing and foiling. And then in this one, we're going to look at fractions with radicals as well as just radicals that are in a division problem. So the first thing we need to know is that fractions with radicals, they can't have a radical on the denominator. So if we had a radical on the denominator, it's called irrational because that fraction would have then gone on and on and on forever. So we can't have that. So what we'll have to do is rationalize the denominator is how we'll call it. So right now I have an example, 3 over root 7. And I want to get rid of this radical on the bottom. It'd be nice if just like the radicals wasn't there and it was just a 7 on the bottom. That would be kind of the goal here. And I want to get from point A to point B in a clever way. So to get rid of this 7 on the bottom, this root 7 on the bottom, we're going to multiply by something special. We'll multiply by a fraction with root 7 on the bottom. You can maybe see where this is going. On my bottom, I'm going to have root 7 times root 7, which will be root 49, which will simplify to 7. But I can't just multiply by root 7 on the bottom. I have to also do it on the top as well. And notice this piece here that I did in red, this root 7 over 7, or I'm sorry, root 7 over root 7, this is actually just 1. It's kind of just in disguise right now. So really, I'm just taking my original problem, 3 over root 7, and multiplying it by a special version of 1, which is the kind of number that I need to make this cancel out. So on my bottom here, I've got root 7 over root 7 is root 49. And on my top, I have 3 root 7. And then my bottom is root 49. That's perfect. So it's going to come out as a 7. And there's what we were kind of goaling for. On the top, I have 3 root 7. If I could do any simplifying here, I would. I can't in my radical, and then my 3 over 7, that can't get simplified at all either. So I'm all done there. Let's try another one then. Say we had, let's do root 2 over 3. So this one looks a little bit different. I've got 2/3 inside the radical. And one thing to note is this is the same as the radical being on the 2 and the 3. So that's one thing to notice is that you can kind of distribute the radical under the top and the bottom. And then now we can see very clearly that right now we have a radical on the bottom and we can't. So we'll multiply by our special 1, root 3 over root 3. And then let's see, on the top I have root 2 times root 3, that'll be root 6. On the bottom I have root 3 times root 3, that's root 9. Simplifying here, 6 doesn't have any perfect squares that fit into it. 9 is a perfect square, so that's going to come out as a 3. So I've got root 6 over 3. And now these two are the same because we've got these equal signs, but this one does not have a radical on the denominator. All right, let's do another one. We'll do 4 of these ones. So this next one looks like this. We'll do root 7 over root 8n. So again, I've got a radical on the denominator. I need to multiply by a special 1, which is root 8n over root 8n. On my top now, I've got root 7 times root 8n. I can put everything under the radical together. 7 times 8 is 56. And then on the denominator, I have everything together again. So 8 times 8 is 64. N times n is n squared. Let's do some simplifying here. So I want to see if there's anything perfect that goes into 56 or 64. And then if you have your chart, you can utilize that. Or hopefully, I hope you know these guys. So 56, what goes into it? Looking for the biggest number we can find, I believe 16 does, but we can check. Nope, not 16. I know 4 works. Okay, is there anything bigger though? I guess not. So 56 and 4. So we can use that. I'm sorry, not 56. 4 and 14. And on the bottom, 64 is a perfect square. So right here, we can pull it out. That'll become an 8. And this will also pull out, pull way over here to be an n. So on my bottom here, I just have 8n. And on my top, the 4 will come break out of jail. So I've got 2 root 14n over 8n. We've done all the simplifying we can with the radicals. The last thing we can notice is that 2 goes into both 8 and 2. So we can make this a 1 and make this a 4. So we've got root 14n over 4n. All right, last one of these type. We'll do square root 75 over 75x over 3. This one looks similar to the last, or this one looks similar to number 2. So first we'll do the breakdown. Root 75x over root 3. And then we'll multiply by our special version of 1. So we're going to use root 3 over root 3. On my top, I've got 75 times 3 is 225. And on the bottom, I'm hoping you're noticing a pattern here. Let's look through the pattern in the top 3 questions we've done. Our denominator was root 7 times root 7, and then we got a 7. Root 3 times root 3 times root 3, and we got a 3. Root 8n times root 8n, and then we got an 8n out. So you don't have to make this be root 9 right here. You can just notice that this is the square root of 3 times the square root of 3, which is the square root of 3 squared, which is just 3. So you can skip that step if you notice it. That way you kind of have one less thing to do. And then on my top, root 225, that is a perfect square. That's 15 squared. So this can come out as a 15. And then we've got 15 root x over 3. And one more thing to simplify, 15 over 3 is just a 5. So this is 5 root x, which looks way nicer than root quantity 75x over 3. All right, we're going to do another bit here. And this next piece is going to look at rationalizing with what we call the conjugate. So I'll show you what that is here in a moment. Let me show you the first problem, and then we'll mess with it. So our first problem will be 10 over. We'll do 7 minus the square root of 2. So let's check this one out. What we're going to do with this is we want to get rid of this radical in the denominator like we were doing before. So what we're going to multiply this time, our special 1, it's going to be a little bit different. Our goal, again, is to get there to be no square roots on the bottom. And to make that happen, we need to make this be a perfect square. So we're going to multiply by this times itself, but not quite times itself. We're going to make this be 7 plus root 2. And the reason why this will work is because we're eventually going to have to FOIL, like these two terms times these two terms. And when we do, our rule with FOILing will end up making these cancel out because of the plus and the minus. So that'll make all the radicals go away, and we'll be left with just a regular number on the bottom. Since we're multiplying by that on the bottom, we have to do the same thing on the top. So the conjugate has a negative, or has the opposite sign. In the middle. All right, so let's check out how this one goes. On our top, we have 10 times the quantity 7 plus root 2. So that's going to be like a distribution here. 10 times 7 is 70. 10 times root 2 is 10 root 2. So got that. And then on our bottom, we'll do our FOIL. I give myself some room. So first times first, 7 times 7 is 49. Outside 7 times root 2 is plus 7 root 2. Inside is negative root 2 times 7, that's minus 7 root 2. And then last I have negative root 2 times positive root 2, so that's minus root 4. All right, let's mess with our bottom here. Notice I've got 7 root 2 minus 7 root 2. Those will cancel. That's what I was going for, is to get the radicals to go away. And then also notice that this 4 is a perfect square, so it's going to actually become a 2. So my denominator here really is 49 minus 2, 47. And then my numerator is 70 plus 10 root 2. So there's no simplifying I can do here. 47 is prime, so there's nothing I can mess with. But that's the game plan here. And if you notice this trick and you want to jump right to that, you can. The trick or the shortcut after you multiply by the conjugate would be to square 7 and square 2 and subtract them. Let's do another. We had negative 3 over root 10 plus root 5. So this time, again, we're going to multiply by the conjugate, which is just the denominator, but instead of a plus in the middle, it's a minus. So whatever it is, do the opposite. So we'll do root 10 minus root 5 over root 10 minus root 5. And I like to put parentheses around each of these so that I know to distribute or to FOIL. So on my top, I'm distributing. On my bottom, I'm doing a FOIL. So on my new top, I have negative 3 times root 10 is negative 3 root 10. And negative 3 times negative root 5, so plus 3 root 5. On my denominator, I have root 10 times root 10 is either you could put root 100 here, or notice it's root 10 times root 10, that's root 10 squared, that's just going to be a 10. Root 10 times negative root 5, so minus root 50. Root 5 times root 10, so plus root 50. And then root 5 minus root 5, that's just going to be minus square root 25 or minus 5. On my denominator, negative root 50 plus root 50 goes away. And then I have 10 minus 5. On the top, I have negative 3 root 10 plus 3 root 5. And that's it. So we've done a bunch of them where we rationalize the denominator here. Some of them looked nice because the denominator only had one term, and we can multiply by that same exact thing on top and bottom to cancel it. And then these last two were a little bit different. We had to use the conjugate. So if you've got two terms in the bottom, you'll have to do some foiling and multiply by the same thing that was on the denominator, but instead of a minus in the middle, it's a plus, or instead of a plus, it's a minus. You just flip it and then foil on the bottom. That is it for 10-2, 10-3. I will see you guys next time.